sponsorship from people like the Health Foundation and others to kind of carry on doing this. We've looked at a whole range of topics across mental health. We did a big event a couple of months ago on inequalities, which is going to be a big theme for us through the next year or two, I think. There's a lot of guidance around the monitoring of inequalities, and particularly some of David Howell's session will be really interesting because it's about kind of finding patterns with people's socioeconomic backgrounds. So that's a kind of key theme for us. But we had lots and lots of people ask us, would you do something on AI? Which is this one. And I've structured it very, very selfishly because I'm chairing according to the way that I think about this. And you can characterize these things any way you like, but we have a kind of lexicon in our trust and through our AI working group of advanced analytics and applied analytics, and everyone uses these terms interchangeably. But what we call advanced analytics is what a lot of people start to classify things like AI as, so things like machine learning and natural language processing and image recognition and those types of things. And the applied analytics, fairly or unfairly, is how I characterize what you're doing, David, which is taking statistical techniques which do exist, but absolutely haven't been used to their full potential. So there are a variety of people probably on this call who can build a regression model out, but there are not a lot of people who can make that go off and do it on its own 50,000 times and come back and tell you the best ones to use and so on. So we have, for better or for worse, taken this distinction of applied and advanced analytics, and that's how we thought we'd set out this first AI in healthcare event. I suspect it will create as many questions as it answers, and that's selfishly useful for us because it then gives us things to kind of come back on. So where we ran an event almost 6 months ago on cancer, that's led to some cancer inequalities questions, which is going to create a timetable for another session that we'll run. So that's me kind of filling to 12:03 to get everyone in the room. We run these strictly to time. We'll make sure we finish by 1. We've got 3 fantastic presentations of about 12 minutes or so. Paul and Catherine and Taz and I will actively kind of monitor the chat, which is always very useful. Please put lots and lots of links in there. The whole premise of these events is that everything is aggressively shared openly. There's nothing behind firewalls. We will write this up, we will publish all of the blogs, and we will publish these videos just on the internet as it was intended. So we're going to make a start. I'm going to, with that introduction, if that's all right, I'll go to you, David, first, and then we'll just work through James and then Parasheth, if that's okay.
Excellent, thank you very much. So nice to meet you, everyone. My name is David Howe. I'm a director of a company called Quantum Analytica. We haven't resided from Cambridge, so we've got nothing to do with that. Just to point out at the start, I'm also director for, have a sort of split role, so I also work for the integrated care system in Surrey as the director for insight and analytics as well. And a lot of these things kind of go hand in hand. So what I'm going to cover in the next 12 minutes is a very précis version of an enormous piece of work that's been underway across the Kent and Medway system. And this has been focusing on lung cancer. And as a bit of a background to this, lung cancer's got one of the worst rates for early diagnosis of all cancers. It has very poor outcomes for early diagnosis. There's no what I call precision screening. It's often quite contentious around this, but a really precise way of being able to kind of target people that are going to develop cancer. There's lots of different types of cancers out there, and only a handful have nice approved screening algorithms in place. Lots of patients therefore end up undergoing diagnostic tests unnecessarily. That in turn increases exposure to radiation, which in turn can also increase your risk of lung cancer. So again, it's not really a sort of perfect world. And so we were commissioned back in April 22 to look at whether we could use some of the advanced analytical techniques that Mark's just described to find a way of improving identification of lung cancer from a screening pool. And this was done on the Kent and Medway population, which is about 1.8 million residents. In terms of the talking about, on pseudonymized patient data and to test this out. We're now moving that onward into we were sort of looking at all of those primary lung cancers, regardless of where they were eventually diagnosed. And in order to do this piece of work, obviously there is a pathway to someone ending up with lung cancer. You know, someone will start off with symptoms over here. They'll have diagnostic tests. They will end up with confirmation of a lung cancer diagnosis, which will then get recorded. And then we have the treatment and end-of-life care downstream consequences associated to that. So what we did was work with clinicians to essentially remove these non-predictive elements. Obviously, they're kind of a consequence, either getting to the diagnosis or the onward treatment. And really everything that I'm about to talk about now looks at the components leading up to someone being diagnosed with cancer to try and pull out some of that predictive power. We did an extensive review using relative risk ratios to understand some of the associations between the cancer diagnosis and some of those historical. And that's skipping over an enormous piece of work that was undertaken to get there. But ultimately, we came up with a number of key characteristics. And long story short, we combined looking at the data with talking to the clinical teams that were overseeing this to try and pull those together. We also looked at research and correlated all of those together to try and create a list of key elements that we felt were useful as a sort of starting place to work with. So they include clearly demographic information, familial history of previous conditions, some drugs. There was actually quite a lot that sat under the drugs perspective, which is we're going off and looking at sort of separately to this program now, behavioural, environmental and mental health factors. So we tried, so we went through quite an extensive process of building some models. We built actually built a solution on top of the Kent integrated data sets that were being used to be able to mine that data around an outcome, in this case lung cancer, so we could try and find the best model or fit. Ultimately, good old linear regression proved to be the most effective in the day and age where we've got many other models out there and lots of sort of interesting stuff. And we think that was kind of, you know, most likely due to the certain factors, your risk of lung cancer increasing almost proportional to things like age or the amount that you smoke as well. So, so that was some of our sort of thinking behind that. We created a prediction model where we created a risk score for every patient within the test set using our kind of standard test trainer data sets to score between 0 and 1 being the highest risk of lung cancer. And what we wanted to do is we wanted to compare that to the current program for screening for lung cancer that is being rolled out currently as we speak across England in a couple of pilot areas, Kent and Medway being one of those. And this is called the Targeted Lung Health Check Programme. And it's quite crude in its sort of application, really. It comes off of a big piece of work that was undertaken in Manchester, and that's being rolled out across the country. So if you're over 55, less than 75 years old, you're registered with a GP, and you've ever had a single cigarette in your mouth, you are part of that screening pool. It's very large. Arguably, we probably don't have the full diagnostic capacity to do that. That's a very large population, even in the UK, where we have some of the lowest rates by comparison across the world. But this was our kind of basis to compare against. So what we found was, through a 7-point combination of grouped features, we were able to determine the most effective outcomes. We ended up with a couple of different models depending on the type of problem that we wanted to resolve. I'll come back to that in a minute. But in effect, we can now take a randomized 30% of that Kent and Medway population, so that's about 364,000 patients in that population. That's with complete data records, just to say, across these different areas. And within there, on average, we would have retrospectively had around 1,800 confirmed primary lung cancers within that randomized population. Using the lung check program, that screening pool was around 56,000 in size that we would be doing through that current rollout methodology. And using that methodology, we would find, again, on average, 581 cancers within that. So using this particular algorithm, if we then take the same, so there was kind of two different ways you could look at this. You could either keep the screening pool the same size and find more cancers, which is what we've got on screen here, or the counter sort of balance for that is we don't actually have the diagnostic capacity to do all of the 56,000. So we could look at trying to find the same amount of cancers through a reduced screening size population. In the end, this was being funded by the Cancer Alliance. It was to find more cancers and keep with the same screening pool size. So using that algorithm and taking the top 56 patients to using the algorithm, we could then find, on average, this was run over 50,000 times, as Mark alluded to, 41% more cancers within that population. These are the grouped and typed features, along with the some risk ratios that we've pulled out off the back of that. And now we're at the stage where we are looking to take this now into a clinical setting, and we are working with the Cancer Alliance, looking to work with a couple of primary care networks or PCNs across the Kent and Medway system, who are currently looking at trialing the Healthy Lung Check program. So it gives us a good control to be able to compare this new algorithm to that one as well. How that's going to be embedded into the clinical workflow is still sort of being discussed. There is the ability to use, so one of the things that we have built off the back of this is as a demonstration purpose is a clinical decision support tool where you can plug in some of these factors real time, and it comes out with a sort of recommendations, whole process though to go through around that for use. The other one is to use this as it was sort of originally intended as a sort of mass screening tool to be done at scale and then ripple down. So that's kind of where we are at the moment. I've skipped over an enormous amount of detail on this to give you a sort of flavour and overview. Happy to answer any questions. We're at 12 minutes, but my details are on screen, and more than happy to have conversations with anyone outside of the meeting.
Really
that was
helpful,
helpful.
David. Really
Thank
helpful.
you.
I mean, the really key point there, which in case people missed, is we don't have to scan everyone, and there's the massive reduction in radiation that's possible if we just pick out the people much more likely, which is such a simple idea, supported by the maths that David's done. I had a quick question, so we're okay for time,
Sure.
David. In reality, I mean, I'm involved in a range of kind of national initiatives to kind of further the cause and the case of the NHS analysts, people like you and I. I couldn't do what you've just done, and I don't think we'll quickly get a lot of people to a point that they can do what you've just done. So I'm interested in how you think we can share quickly in a safe way as well. So is that reproducible R code? Is it different sort of training? There's work going on around AI, which we're going to see today, but we're not realistically going to get that into the toolkit of the jobbing NHS analyst quickly.
Yeah.
But you could pass them a product, but we don't want that to be a black box that then people don't understand. And I'm just interested in your views about that.
Yeah, I think it is a tricky one, to be honest. So, there are a number of communities, and I think, well, certainly speaking on behalf of Surrey and others that I speak to on a regular basis, everyone's trying to set up their, analytical insight communities and groups to share best practice. But I think there is a lack of skills and capability out there to do some of these things. In Surrey, we are working sort of very small scale, starting just doing really, really simple models to very simple problems, just getting a really good kind of process in place, getting people to understand some of the logic to that. But really, it is quite a journey, I think, to sort of take people along. There are already a lot of code sharing sources out there now where people are sharing, certainly a lot in R. We've written ours in Python. So again, there's kind of, mixed currencies of, what people are learning out there. But, I think things like this are really good actually to share what people are doing across the country, and always happy to, help others out there trying to do the same thing in other places.
Yeah, that's really helpful, David. You've got some specific questions in the chat. I'll let you do those sort of offline around why linear regression popped up and so on, just to sort of keep us moving. I'm going to move over to James once he takes that call. James, all yours. So I'm hoping this will be a nice sort of kind of AI journey from kind of relatively traditional use of data right through to sort of imageries that Parachet's going to save, and with sort of James in the middle. So over to you, James.
Can everyone hear me?
Yep, loud and clear.
Okay, so I'm just going to expand the screen. So, okay, here we are. Okay, so this is a slightly more higher level than what others have, what was discussed before. I want to talk about the data systems which allow things like what others want to do around applied analytics and as well as the advanced analytics of others. So I've been at King's College Hospital for nearly 10 years now. And I've spent a long time trying to modernize the systems from the inside, which I'm sure you appreciate the difficulty, Mark, in your life. And I think the real goal here is that my interest in the AI and digital health, and also we are very interested in using it for improving clinical care. I think the actual near-term benefits are really about efficiency gains. Because I think a lot of the AI healthcare AI tools that we have nowadays are designed are not good enough for safe clinical decision support yet, but they're nearly there. But it is definitely available for improving efficiency, and that's what I like to focus on. So while others tend to kind of focus on the top of the pyramid, I would like to focus on the bottom three layers, which is big data, analytics, and data science, and the infrastructure right at the bottom, because all that needs to be sorted if there's any scope of building the thing at the top. You can build fancy algorithms at the top, but if the bits at the bottom are not sorted, it will never scale or translate. And so it's better to build the things at the bottom first, in my view, or at least put enough effort into them. And that's what I think the focus should be. And so you need to to do this properly, the applied analytics as well as advanced analytics needs to be generated. So you can, as I said, develop algorithms. You can clean and sort and arrange data from a data set and then generate an algorithm. But to use it, you need to do it in a way that is continuously and rapidly. And for it to be continuous and rapid, you need the pipelines, you need the APIs, you need the data to be sorted and cleaned very quickly. And EHRs, the stage of our EHRs are not in that. Many of them are not in that state. Many of our systems are not in that state. It's not just the EHR, there are many database silos. And so a lot of effort has to be done to reverse all the wires that we have built and untangle them and make them scalable. So the original way we produce data is very traditional. It's kind of copied from our paper flow, our legacy processes. A clinician writes into paper notes, the paper notes gets compiled. Some other people by computers transcribe it, populate spreadsheets, populate forms, put it into other systems, and then generate reports in a quarterly way. This method worked very well in the 70s and 80s. We, however, have modernized and replaced all that paper bit with computers in the middle, but everything else is the same. And so what we're actually having is that we've actually made the process slower because it's harder to interact with the computer. We're actually creating a lot more clicks. And that's what human beings are complaining about. We hate clicks. We aren't really making use of the data, and because that there's a second step over there, as you can see, all those guys on the computers are manually processing data. I've heard some people call it a mandrolic system. We are using human beings like robots when we should be using robots like robots. And what I've been working a lot on these processes to automate that second step. So traditionally, you would have scripts and such to transform the data. I've been using language processing as well as semantic systems to put them into, to sort the data into a big lake. And then once that's done, we have unlimited, well, not unlimited, but, real-time, free-flowing data, and we can stop worrying about people having difficulty plugging into systems. And then the data can then feed back, and that you would have this positive feedback loop, a virtuous cycle in which new data generates new insights real time or near real time, and algorithms can scale. And so to do that, you need to build all the architecture. So the first step we did, I did back in 7 years ago now, was we set up this thing called CogStack, which essentially is a big data lake of unstructured data. We've open sourced it. All the documents, papers, scanned documents, free text, Word documents, PDFs, radiology reports, histopathology reports, we ingested out of the a traditional SQL database and put it into a searchable index. And then that was initially for the purposes of the 100K genome. But then because we had all that text, we could do keyword searching, and then we migrated very rapidly onto what we call MATCAT, which is a natural language processing tool that we've been using to process that data. So to add meaning to the data, not just handling text. We started, as I said, way back then. The green arrows at the bottom shows the different models, natural language models, which are being built over the last decade globally. And the latest ones are ChatGPT being very exciting in the last week. But what we were doing at the same time. And as you can see, the pandemic hit just at that exact moment for us when we had managed to finish our NLP components, and when a GPT-3 language model became available. And we were then able to begin a lot of our large-scale language training on NHS data within the trust in a safe environment. We have probably the largest amount of healthcare language that we have encountered anywhere, largely because we just happen to be inside the trust, and with high-performance computing. So this, for example, one of our models we can do it. It can run in real time, and it would detect obviously the text, including typos, as you can see, as well as acronyms. We can train it. It would also be able to detect negations. So As you can see here, it has metadata about when it occurred, that the night sweats is no, and that the lymphodenopathy is a negation, that it does not have, and temporality and things like that as well. We can obviously run this in real time like this. We can also run it across everything, and we have run it across everything. And it takes everything in KCH means everything for the last 20 years across all our electronic health record systems, archaic as well as current. That takes 2 days. And so we can actually do this repeatedly. And so we train it, we mark its answers with our system, and then with junior doctors or research nurses marking whether it's correct or wrong, whether it's detecting the correct words and meaning, and then we retrain it, and then we rerun it across everything again. This was quite amusing during the pandemic because it hit us at the right time. COVID didn't have a common name at that point. There were various terms like nCoV, COVID-19, SARS, Wuhan virus, various terms like that. And we ended up just being able to kind of conglomerate all these searches with in real time and generate these real-time feeds. So those things that they highlight, we can generate automated feeds on the left at multiple hospitals, it essentially being like a Twitter feed of what doctors are typing into the records. No one has to fill in any extra forms. No special COVID form and infection control form. They just type what they normally type or dictate what they normally dictate, and our feed detects it in real time. And it worked reasonably well. And it actually precedes the lab samples by about 12 to 18 hours, which is unsurprising because you get symptoms before you get lab tested. It's obviously not a perfect signal, but it shows what is possible if you lake data in real time at large scale within an institution. We are now moving to the next stage. So some of you may have seen the ChatGPT in the last week, which is basically a chatbot made by OpenAI trained on large amounts of text, open text. We have, in addition to that language model that you've seen, we have begun to try to autocomplete a patient's future. Because just like you can autocomplete a sentence in an email, if you extract all the meaning from it, and then you can feed that into a second language model, which can then try to autocomplete what happens next. We've got a preprint out a year ago, but we've been working and tuning it in the last year. We intend to release this demo in the next sometime this month. Essentially, you can have a bit of text. You can ask it to generate next forecasted possible diagnoses, problems, medications, procedures, symptoms, and we can do this with in a probabilistic matter. We're not planning for this to be used for clinical decision support. It is not suitable for it because it's trained on historic data. Historic data means it's historic activity that has been. That doesn't mean that it's a real world things now. It's not necessarily relevant now, but it shows the power of transformer models and language models to be able to generate these timelines. And we plan to use this for simulations, and we've tried to set exams and such for it. Okay, that's going on. This is the AI Center, which I'm sure Parashka will talk a little bit more about. This is around a machine vision element, and we have a large number of trusts that we partner with and third-party startups and academic partners. And a lot of this is around building the same thing and the infrastructure for images. And images is helpful in that images often come with labels that radiologists generate all the time. We need to do that at scale. So one goal is to make AI. Well, another goal is to make systems that allow AI to be deployed and used, and lastly, for evaluation. I would say that they are different things, and we need to think of them differently. I'm only going to focus on the middle one for purposes of time. So we have earlier 2 weeks ago at RSNA, which is a radiological conference in North America, really announced the release of AID. AID is a deployment engine which acts like an orchestration system for AI models. It uses an open framework. We have open sourced it on GitHub last week. and it essentially takes over the job of people training a model. They just package it in a way, and then within the A8 system, it can plug into DICOM servers, PACS, file messaging, and such. And so it takes over the hard task of training building the whole software around the AI model. This is therefore acts like a bit like an app store for different AI models. I think this is the kind of things that helps bridge that translational divide between all these little AI systems which have difficulty scaling, and also a hospital not wanting to buy 20 different AI virtual machines and maintain and having a single one with lots of containerized models which can orchestrate between them. So I believe EASCAN has received one of the outer framework for this, and we will begin to encourage people to build these models within that space. Obviously, we do use a lot of open source technology. We believe in open source. There is a role, obviously, for proprietary informatics systems. Obviously, most trusts use the ones on the left, but we need to make it work together. It's not either or, it is both. I'm interested as well in terms of equity, and we have generated natural language dashboards, which are available openly everywhere for people to search PubMed in a natural language supported way to track which areas are taking off in AI and which parts of the world are contributing more to open access journals and publications in AI. Breeze through this really quickly to give more time for others. Hopefully that's a good enough sum. And yeah, the key bit really is that it's not just building AI; you have to embed it, and that is actually the heart. That is a significant part. It's 90% of the work, really, embedding it in. Thank you.
Yeah, really interesting, James. Thank you for coming along. I've asked you and David a question. Well, I'll put it in the chat actually, but I'll ask now because we're okay. I'm just really interested in my role in EASCAN. I'm constantly trying to enforce better data quality, and enforce logic within our tools and our EPR. You know, are you on an RTT pathway? Then you have to fill in these forms. We can't have any patients that are 200 years old. We can't have any patients that have been admitted in the future, and so on. And that's what I feel like I'm kind of living and breathing. And that is analogous to your early slide with all the case. You could, if you're being facetious, sort of characterize what you then went on to say is you don't need to worry actually, because we'll just train it that chest, as I put an example in the chat, chest-frac is the same as fracture of chest, and you illustrated that with a kind of COVID example. So I'm just kind of interested and interested in your view as well, David, because you can't do this neat and tidy quantitative data to build your regression model. Do we still need that, and to what level, or do we just think it doesn't matter if data quality is not very good because the machine will learn what it should have said? It will identify that it was a female because of something else that happened previously, and it will then populate the gender, and so on. So maybe
I think you do need to do some enforcement. So the issue is that at the moment most EHRs are designed around being checklist activity. We're using the EHR to make people fill checklists. That's a process thing, not a data thing. We're not interested in the data. We're making them doing a checklist for that. I think we probably have to have, I think you can probably get about 80% of the way with forms and structured data, and then the remaining 20% with NLP, or kind of suggestions-based approaches after that. But we probably shouldn't be whipping our clinicians and juniors to fill in data properly, because that I don't think is a good way of making use of their skill. We should be using to articulate what the clinical problem is, a lot less copy pasting, and a lot more traditional clinical thought processes and data entry.
Very, very interesting. That would be a longer discussion. David, did you want to come in really quickly?
Yeah, I was just going to say, I mean, I think, what I'm certainly seeing sparking up, and what I'm being asked for a lot now is actually kind of, using machine support, as we've kind of, as we've just seen really through some of the stuff James has been describing too. help the improvement to coding, and using sort of machine learning to actually kind of identify patterns where data is, you know, wrong as well. And it comes at sort of a couple of different levels. You know, there's obviously providers needing to sort of, you know, improve data quality themselves, either for internal or for sharing that outwards to others across the system. You know, we have coding on one side for someone that's got a long-term condition that another doesn't have, and it's kind of how you also then ensure that you're getting that joining up across different sort of you know, provider data sets, I guess. But you know, shared care records, I think, are starting to try and get us on that journey towards that.
Yeah, I mean, this secure data environments that we're all going to be working on is going to be an attempt to link all this together, and actually literally for myself, you, James, and Parashev as well, because we're going to have a whole range of data that we're not kind of used to handling, the scans, the metadata, and so on. Okay, Parashev, thank you so much for joining. We're fine for time. I've tried to create a link in my mind, and if it only works in my mind, between what it's done around kind of speeded up traditional use of statistics, James laying the ground, and then you showing us some of the image work that we're starting to do now. So over to you.
Thank you very much. In fact, I was going to talk about images, but I thought actually it might be better to talk about something that's conceptually very different, which is machine prescription. So let me just share my screen, and here we are. And maybe you can see that. Yes. So what I think would be helpful for us to think about is, what is the central task of medicine? Well, it's of course prescribing, it's treating. And we're actually surprisingly bad at interventional innovation. Here is a chart of the cost the cost of each drug that actually reaches the market, $1 billion worth of spending. And if you can see that it actually has been going down, the number of drugs we've been able to deliver to the market for each $1 billion worth of R&D spend has been going down. And this is actually a logarithmic scale. It's actually halving every 9 years. And if you look over the same period, the number of publications on PubMed has been growing at the same rate, but in opposite direction. So it's clear that the efficiency at which we bring drugs to the market, as an example of an intervention, is poor. Now, why might that be? Well, we are, of course, in medicine treating individual patients, not populations. And yet, what we need to do is to learn from large populations about what to do with the specific individual. And the way in which we do it currently, as exemplified by the standard randomized controlled trial, is to take an average, take the average of the population and essentially make inferences that relate to that mean. Here we have the average of all cardinals of the Catholic Church on the right, and here we have an individual cardinal on the left. You can see that although the average has similarities, it's clearly not a very good indicator of what the specific individuality of that patient is. So let's imagine that we have a simulated condition of some kind, which I've created with a Photoshop filter. If we were to take the average of the population as our reference, then the result would be very poor indeed. Now, if a plastic surgeon produced that kind of result, we would, quite possibly strike him off. And yet, this is the gold standard for how we do medicine. And this is what we consider to be the best that we can achieve. So what is the alternative? Well, we could try to capture the individuality of each patient by a more detailed, a richer, high-dimensional multivariate parameterization. And the technology that James has been describing provides that possibility right now. We can take obviously images, but also free text, anything else that any of the rich data that we capture on individuals and model them explicitly. So seen that way, the introduction of complex models isn't really a deviation from what medicine has always tried to do. And it certainly isn't a mechanization of what medicine has tried to do. It's rather about humanizing what is already mechanical, what we have already formulated as essentially an algorithmic form, because that is what the interpretation of a randomized controlled trial is. So in effect, the application of complex models makes our intelligence much more flexible, much less artificial than what evidence-based medicine currently prescribes. And so actually it ought to lie at the core of what we do in medicine. It's not really a luxury. It ought to be part of the staple. So let me give an example of how one might use complex modeling in order to achieve better interventional outcomes. Here's an example from chronic migraine. Now, headache, I suppose, is often dismissed as being something that's a mere symptom, but it's actually the second most disabling disease worldwide. If you quantify its impact in terms of years of lost life owing to disability, a headache is actually quite pronounced. So here is a plot from the Global Burden of Disease website of the contribution to years lost due to disability of headache in comparison with others. And you can see it's a large chunk of the total landscape. So why is this so difficult? Migraine is probably the dominant cause here. Well, it is partly because the underlying nature of migraine is highly heterogeneous. There is a huge number of components to defining the migrainous phenotype, and this is true of primary headaches in general. Here is a list which you're not supposed to be able to read. The point here is that it's huge. The number of potential features that define each individual is very broad. Equally, we have a wide range of drugs that we deploy because none of them works particularly well for all patients. And what we have to do is go through a very slow iterative process where we move from one drug to another and one that works for a patient. So how do we select the right drug, especially given that the duration of evaluation of each drug is typically at least 3 months before you know whether or not it's working? Well, one can follow some guideline. It could be a nice guideline. It could be a guideline from another source. One could ask experts, or one can be based on price, or indeed one can just choose a random selection in terms of the order at which one gives the drugs. And if we do that, we actually end up with roughly the same time in months to effective treatment. It takes often more than a year before you actually hit on a drug combination that works well. And this is from an analysis of 1,400 patients at Queen Square, conducted with collaborators at Queen Square and also in Norway. So actually, currently, it doesn't really matter what you do. You end up having to endure many, many months of pain before you find the right drug. What can we do better? Well, what we can do is we can parameterize the phenotype of each individual, NLP-based analysis of the patient's clinical record, and train a causal model that learns what the conditional outcome of a given treatment is across the space of possible treatments. And this is using large-scale observational data. Still relatively small here, only 1,400 patients, but it's something that could easily be scaled. And what we can show is that across the range of drugs here on the x-axis, we get different individualized treatment effects if we were to look at the mean of the population as a whole, which is the red violin plots, versus the mean of the subpopulation that our causal model predicts is likely to respond to the drug. And this is out of samples, so this is not incestuous in the way in which inference is made. This is reliable. So what you can see is that across the full range of drugs, the predicted group, the group that's predicted to respond better, does indeed do better. And so what we can now do is produce a machine ordering, a machine prescription system that selects what drug you should try first. The idea being that you should try the drug that is most likely to relieve the symptoms in this specific patient. And if we do this, and we add this approach to our plot of the time to receiving effective treatment, we find that we save, on average, 3 months of pain. And this is not we choose expensive drugs, for example, ones that have more pronounced side effects. This is simply because we can select the right drug for the right patient. This is still observational data, but without a sum prediction. We haven't yet evaluated this prospectively. But the magnitude of the difference between what the causal model predicts we will be able to achieve and as I say, current practice is substantial. So it's something that would I think very easily motivate the performance of the formal evaluation when we look at the impact of this perspective. The details of this analysis were recently published in a paper, as I say, this collaboration with colleagues in Norway and also at Queen Square. And the point here really is that the richness of the underlying data and the complexity of the driving relationships that determine outcome and also determine susceptibility to treatment is likely to be, for most conditions, much, much more complex than we allow. And so really not to think that medicine is a lot meteorology and it is like horology, which is the current way of thinking about it. And if so, the approaches that have been successful in predicting the weather may well end up being the approaches we'll actually have to adopt in thinking about outcomes, predicting outcomes, and crucially predicting what the optimal interventions might be in medicine. And if that's the case, then we're going to need vast amounts of data, as James has shown us, but we will also need very substantial compute and much more detailed attention, much more intense attention on the kinds of modeling that we deploy and complexity and sophistication of the models that we use. And so the change that's required may actually be a very substantial one, but it's one that it seems to me is urgently needed, because what we're trying to do here is achieve a very difficult task, which is to make predictions about single individuals from information that's deployed across a wide, that is drawn from a very wide range of patients. And so capturing that heterogeneity is always going to be complex. But it is something that we have to do because that's what medicine really is, and that's what it's always has been. I will stop there.
Really, really interesting, Paris. We're fine for time. If anyone's got a question, I might take chair's prerogative and start, if that's all right. What are the breakthroughs that we need to speed that up? If you kind of come across into, I'd say David and I's world of a kind of jobbing NHS analyst and the Goldacre review, and we are very interested in proactive sharing of code. So I think through initiatives like this and others, people are getting that there. We need anything you do, you need to kind of proactively share. It sounded as though you were alluding to some of the issues around the costs of cloud computing and things like that as well. What are the breakthroughs that you think will get us there quicker than we might do at the moment? And sometimes COVID does that. We suddenly saw all our outpatients virtually and the world didn't stop. Are there other breakthroughs coming that are commercial ones or philosophical? What do you sort of you're describing that issue? What do you think might be the things that speed it up for you?
Well, I mean, the focus at the moment is on the technological aspects. How do we actually do technological innovation in the NHS, which of course historically has been very bad at it. But it seems to me that a great deal of the innovation is in the realm of the underlying concepts, how this is about individual patients. And there is actually a philosophical task here to move away from the way which would be to think having evidence. We have been taught to assume that the way to describe individuals is only in very simple terms of the small number of variables that are sufficient, that typically you could only have in order to run something, a randomized trial. And so discarding most individuality as we say the best we can about anyone that he or she is some distance away from the average. And because that's so deeply ingrained, it's now very difficult for us to persuade, well, the medical community, but regulators in particular, the right approach is different. The right approach is to try to localize the neighborhood of each individual patient with as much precision as one can, taking into account everything that you know about this person, and then make a decision based on that. And those sorts of decisions are going to be exclusive. You will never have proof that something works for everyone, or indeed that it works for a given subset. There will always be a better model around the corner. And the task, our task, is to make sure that we have the best model that the resources that us give us. And this is why I think the historical aspect is interesting, because that is how medicine used to be. Except instead of a formal model, you would have a clinician who would learn by experience and then would apply that experience in managing individual patients. Now what we can do is essentially embody that within a statistical model, a very complex statistical model, but nonetheless a statistical model that can be replicated, that can be interrogated, that can be evaluated, and so on and so on, and that can continue to learn beyond the limited length of a clinician's career.
Yeah, interesting. Yeah, there's various applause in there. That's brilliant. Tom, do you want to just come off mute for your question? We're okay for a couple of minutes.
Yeah, so I think this is really what was just said. That pharmaceuticals have established evaluation, but is what people are looking for. But what you were sort of hinting at is you were in sort of stages of development of this, and you were contrasting with certain types of data. And I wondered if you'd formalized that into sort of phases comparable to these files, or is this just the way you're thinking about this? Because this philosophical question is quite important, but we need to start writing this down if we want a regulatory approach. Are you doing that, or is that just your personal reflection?
Well, I think we are at a relatively early stage. The notion of individualized treatment effects, of modeling complex heterogeneity in populations, in inferring interventions, optimal interventions, is new. I mean, obviously causal modeling has been around for a while, but its application in this context is very new. And the regulators are having a hard enough time coping with prognostic models that are learning at individual level, that are not easily evaluated in the current framework. And of course, prescriptive models are one layer above that. So before we can codify a process, and I agree, it's essential that we come up with something that can be written down, that can be referred to, that can be a reference. I think what we need to do is to clarify the conceptual ground, persuade the community that evidence-based medicine was a great idea for the technological possibilities of its time, when the only thing you could do was run ordinary statistical models where you could never have data that was both rich and large scale. You had to sacrifice one or the other. Then conventional evidence-based medicine was the only thing you could do. But now with extraordinary frameworks of the kinds we've just seen, one can have one's cake and eat it. You can have large-scale data, have rich data, and you can make it computationally tractable. But that realization is going to take some time to arrive. But I think it has to arrive, because every day where we treat patients as if they're averages is a missed opportunity. Because the reality is Mr. and Mrs. Average do not exist. We are treating what are inexistent statistical entities. We need to focus on the individual, and we need to do that as a priority, not as something that's an embellishment on the way that medicine is done. That has to lie at its heart.
Thank you, Parash. Yeah, what a brilliant session. We're out of time. Thanks to our 3 brilliant speakers. I didn't know we were going to end on a picture of an average cardinal, so I might pop that on Twitter just to kind of mark the day. Very, very grateful for you 3 appearing. We'll publish all of this online. We'll write it up and we'll send it around. And just all of you do share, but also just let us know from this if there's other specific topics within it that you'd like more detail on. It just creates the events program that just keeps rolling forward. So thanks ever so much, everyone, and we'll keep in touch and see you soon.
Thanks so much. Thank you.
Thank you all.